All right, we've heard some very nice talks about the use of chemistry to address challenges in biomedical applications and the study of chemistry in cosmological context. As we look towards the future, we realize that modeling and computation plays an integral role in each of those areas. And as those arenas are increasingly sophisticated and the questions are more and more advanced, the computational requirements scale quickly. And so we're looking at building hardware of the future to host these future discoveries in a variety of different areas. And to do that, you're going to need organic materials. And so that's what I'll discuss today, designing materials to enable that future. Before I go into a brief bio or introduction of myself, I'd first like to thank the organizers for hosting this symposium and all their hard work for putting this together. I'd also like to thank Bob Allen. He's the Senior Manager of Materials here at IBM Almaden Research Center. And he's been a fantastic mentor that's really opened up a lot of opportunities for myself and younger scientists. So thank you very much, Bob. In 2013, I completed my PhD in macromolecular science and engineering from Case Western Reserve University as a member of Stuart Rowan's group. And this was supported by a NASA graduate student fellowship, and I was co-advised by Michael Metter, the Director of Materials at NASA Glenn at the time. And during my graduate work, I exploited supramolecular interactions to template the synthesis of a non-natural product, a poly-N-catenate. And this unique polymer was based on a mechanical bond, and essentially you could think of this like a molecular chain. It was during my studies as undergraduate and in graduate research that I really saw the impact of IBM research. I was familiar with some of the most remarkable work that they published and the high-profile research that really pushed the limits of nanotechnology. In projects such as the millipede, where AFM cantilevers were used to manipulate a polymer surface to create a dense memory array, or manipulating individual atoms to spell out IBM or create a quantum chorale. So it was really a dream to be a part of IBM research. And as I was completing my graduate work, I was fortunate enough to have the opportunity to join Al Nelson's group, who was a manager of a self-assembly group at the time. And I worked under him as an advisory engineer to manage and leverage NMR hardware to advance research in a number of different project areas. And it was after he left to join the faculty at the University of Washington, I joined Dan Sanders' group and essentially reinvented myself in this research interest to connect materials to solve some of the ongoing challenges in IBM hardware. And this is what led me to where I am today as this manager of novel electronic materials, devices, and process technology. So let's first talk a bit about nano fabrication. This is really a critical foundation used to make a variety of different devices. And what I feature here is the IBM Power 9 processor. So this is a processor that contains over 8 billion transistors. And recently, IBM's announced the Power 10 processor with now 18 billion transistors in the same unit area. The backbone of device fabrication uses patternable materials to create these transistors at the very small length scales. And we didn't just start by printing at the single nanometer feature sizes, but we've come a long way since the introduction of microelectronics. And these have really relied on polymeric materials to really push the resolution, to push the ability to pattern and fabricate devices to where we are today. And so as I think of it, materials are really the enabling component, or one of many enabling components that get us to these amazing computational power that we have at our fingertips today in our cell phones, and that we're using today to host events like this. It is, however, becoming increasingly clear that there is an additional future that we have to think about. After we get past 7 nanometers, there's discussions of a 5 and 3 nanometer technology node. After you get to those single nanometer feature sizes, the future of computing is going to look very different. So this may involve our traditional bits as we're familiar with, transistors. There may be other architectures that provide access to different types and different computational power densities, such as this IBM nanosheet transistor. But we've reached a point where we can look to the future of the landscape of technology and the future of computing. And we see that this new foundation is going to incorporate not just those traditional bits, but also integrate things like artificial neurons. And this is a picture of the Summit supercomputer built by IBM. And essentially, we think of this as bits plus neurons as a system. So this is a special type of supercomputer that can take advantage of not only CPUs and processors, but GPUs, make a system that's capable of learning, inferencing, and steering, and one of the most advanced to date in this. We also see the emergence of other types of computational architectures, like quantum computing, that takes advantage of superconducting circuits that behave like artificial atoms. So with these, you can manipulate them and take advantage of these quantum mechanical properties like superposition and entanglement to address increasingly complex problems like modeling chemical systems. And these are poised to solve problems that we may consider intractable with traditional computers today. So like the advancement of the technology nodes that were enabled with these chemically amplified polymer resists, so too will this landscape of future of computing draw from materials to enable, optimize, and improve these types of systems. So while we're working in each of those different areas of AI, quantum, and your traditional bits, I'll highlight one area that I can discuss in more detail, and that is addressing some of the existing problems that we have with making devices, but wiring to them. So on the left-hand side, this is an image of a typical wiring to device. So you might be able to print a 7 nanometer feature, but bringing the outside world to that and connecting to that can be very difficult. And it relies on multiple levels of patterning and then alignment. So if you place a wire or a via onto your device, you need to place that in a very well-controlled on top of your metal level here, labeled M1 V0. If you're off, if your alignment's off, even slightly, you can introduce variability into the device performance. If you're off even slightly more, you can short devices, which impacts yield. And so if we could find a way of instead depositing a material in a selective manner instead of having to do this type of alignment, that would provide a huge advantage in terms of being able to connect our devices to the outside world. And so part of our work was looking at a selective deposition or a selective alignment, where you could take advantage of a surface composed of dissimilar materials and exploit the chemistry of those surfaces to block deposition on one and not another. And thereby you could have a correct placement without having to do this patterning step. And while this field of self-alignment is not new, the use of custom and synthesized materials are growing in terms of the interests. So one of the things we did is we took a material that's very effective at depositing and blocking thin films and the selective deposition of those. It's this green molecule you see pictured to the upper right. Now, after so many, such a thickness of film that's deposited, you'll start to see your loss of selectivity. And we started wondering if we could address this loss of selectivity and understand the relationship between selectivity and the material by developing our own types of inhibitors. And so we looked at a variety of different types of interacting, either through pi-pi stacking and hydrogen bonding, or a variety of other types of interacting components to realize a more selective process, or a highly selective one that you see in the lower right-hand corner, using the same conditions. Now, we also see people start to, and are using not just planar surfaces and planar structures, but are resorting to three-dimensional types of electronic devices. And if you want to use a small molecule like this, pictured here, this hydroxyamic acid, it's very effective at inhibiting the growth of zinc oxide on a planar film up to 500 ALD cycles, as it's labeled here. But after that, you start losing selectivity. However, if you just take that planar surface and add topography to it, there is a complete loss of selectivity. That is very difficult for these small molecules to cover corners and edges. And so we've developed a way of selectively polymerizing from a metal surface a neuroborane type of polymer that's very effective at inhibiting those very rough surfaces, or surfaces with feature sizes that are out of plane. And this allowed us to deposit selectively in the trench of, or bare silicon surface of this structure that you see in the lower right-hand corner. And we've demonstrated this at large scale, showing that we could very well control this polymerization and guide deposition to a Sierpinski-like fractal pattern. So looking beyond what we can do additionally with the materials aspect of these selective depositions, we looked at if there's an additional level of control that you may be able to exert with that through patterning types of steps. And this is what we describe as additive lithography, or an additive process where you can introduce a material as opposed to a subtractive method of lithography or a traditional approach to that. There may be advantages in this additive approach such that you do not have to subject a material to a high-energy etch process that may amorphize sidewalls or lead to damage to your material. This also gives you the control that you would not otherwise have in a selective deposition that is a simple reflection of the underlying pre-pattern. And so this tailorable area selective deposition using this exposure technique is one that gives additional benefit to traditional methods of doing this. And so we found that by tailoring our packing density of these types of inhibitors, we could control this process very well. And with an underlying pre-pattern that you see in this schematic pictured, we can selectively irradiate areas of these inhibitors and block deposition to spell out IBM, for instance. And we can see a dose dependence, or a dependence on how highly cross-linked that film is, and how well that translates to blocking any sort of film growth from those areas, as well as arbitrary feature generation. And so this gives us more control than one might have from just an area selective method of providing a film. And so with that, I'll conclude. This is a lot of work that's been contributed to from a lot of great and fantastic researchers. And so we've done a lot of this together with our colleagues at IBM Semiconductor Research. And some of the characterization of that last portion of being able to pattern our monolayer materials and generate different types of features are characterized and exposed at Lawrence Berkeley with our collaborators at CXRO. With that, I'll take any questions.
Thank you so much, Rudy, for another fascinating talk. It's been great to see so many different kinds of chemistry throughout the day. Because we are so close to time and there's another session after ours, I think we're going to skip the Q&A, but thank you so much for joining us today and sticking around to hear all this great science. Goodbye.